This is the fifth talk in the series. Today we have Naren Ramakrishnan, who is going to speak with us. He is, of course, one of our team members and a longtime colleague of all of us who moved here from VT to UVA. I know him for a long time, just a superb data scientist. And he led a very, very important project with IARPA some time back that did tremendously well on building data-driven methods for forecasting and situational awareness for various social, political, and health-related topics. And Naren, please go ahead. He's been working on epidemiology for a while as well with us.
Great. Thank you, Madhav. Good seeing all of you. So many of you are co-authors on this effort. And following up on what Madhav mentioned, this slide used to have only 2 logos. But now we have 3 logos. Just to set the context for what we're going to be talking about today, this is a project that's focusing on information extraction from news articles. We are trying to do automated reading of news articles. And from these news articles, we are trying to extract key epidemiological information that would be useful for modelers and forecasters. The talk itself is not going to be doing any modeling or forecasting. We're simply talking about how we can extract key information that would be useful to disease modelers. One of the important aspects here is the notion of what is called a line list. A line list is basically a tabular listing of key patient information, such as shown here. It includes information such as age, gender, the onset of symptoms for a patient, when the patient was hospitalized, did the patient come in contact with any wildlife or animals, did they have contact with other patients, do they have comorbidities, and what was the outcome for the patient, did the patient recover or not, and so on. So this is especially important to do this level of deep dive and tracing of information at the outset of disease incidents. So this is an example of what a line list is. And for an epidemiologist, this is very useful information because once you have this information, you can start posing and answering a lot of important questions about disease spread, mortality, and so on. The goal of this project is to see if we can digest a lot of news reports at scale and try to extract information like this for use by epidemiologists. So typically line lists are curated manually and they require a lot of human supervision. And the typical way in which people have done this past is to be able to go through each patient individually, try to interview them, ask these questions, or if they are reported, to be able to manually start curating this information. And there's a significant need to automate this process, especially as you have emerging outbreaks across the world. And even though there are news reports that are constantly being released and issued, there's not much effort being focused on trying to extract this type of information, tabular information at scale. So this type of information extraction is very popular in a lot of other domains. So people have been doing information extraction for finance, information extraction in political science, information extraction for even cybersecurity incidents that are reported in the public news. To the best of our knowledge, this is one of the first efforts that's trying to look at disease incident reports and trying to extract information of use to modelers. This is an example of how the full pipeline works. On the left, you see a set of news articles, and highlighted in those news articles are key facets that are of importance to a disease modeler. So they include information about the gender of the patient, the age of the patient, what date they were admitted, and before that, what date they developed their symptoms, and any relevant history for that patient. And we are developing this approach that we call GEL. And the goal of GEL is to come up with this table on the top right. And once you have the table on the top right, then you have a lot of information to be able to plots like shown in the bottom. You can plot a distribution of the ages of the patients, the genders and dates and so on. So think of GEL as supporting this missing link to go from news articles to providing this information and going forward. The first strategy that one could do is what we call seed predictors. In this project, I'm going to show you some examples with the Middle East respiratory syndrome, but you could take some of these ideas and apply it to many other diseases as well, including COVID. The idea here is, suppose we have a set of important features that we would like to use as seeds to extract some of these facets of interest. And these seeds, we use them interchangeably as predictors. So the seeds are essentially the ones that tell us which sentences are relevant from the full news article. And the seeds are typically provided by domain experts because that's typically what they search for. One could use the seeds as a starting point, but they won't be sufficient. They can help you guide the extraction process, but they won't be able to trap all the situations in which people describe these incidence reports. As an example, you see in the bottom of the slide, onset is a seed or a predictor for the onset date. So that keyword is often used alongside the point where people talk about when the patient started exhibiting symptoms. Similarly, hospitalized is an important seed keyword to know when somebody got hospitalized and what happened to the patient subsequently. So think of seed keywords and seed predictors as a starting point to begin your information extraction, but they're not by themselves sufficient. Here's an example of some of the seed predictors for many of the features that are of interest to us. So as I mentioned, we are focusing on MERS, and we'll focus particularly on reports from Saudi Arabia because that's the data set for which we have ground truth available. And these are the aspects that we would like to extract. We'd like to extract information about demographics, the onset dates for the disease, the outcome, the hospitalization, and so on. And then we want to identify a whole range of clinical features for that particular incidence, including whether the patient came in contact with animals, any secondary contact, comorbidities, and anything specific to the healthcare workers, and so on. And on the right, you see the seed indicators that people use. These were suggested by epidemiologists. And like I said, these are not sufficient, but they provide you a first starting point to try to extract this type of information. So this is the overall framework for this GEL methodology that we have. We start with the WHO MERS bulletins that we are getting, and these are public. There's a whole range of pre-processing that happens for these news reports. There's tokenization or lemmatization. There is splitting of sentences because sometimes these sentences are compound sentences and you're better off splitting them and then analyzing each of them separately. We want to extract specific phrases pertaining to dates and locations and so on. And then we go through a series of modeling, and we use different levels of modeling to extract various features of interest. The age and gender are sort of the easiest to extract, and we'll get that out of the way first. And then we want to talk about extraction of disease onset and all the clinical features. And we call these level 1 and level 2 because they're a little bit more involved. And we bring in a more heavy-duty machinery to bear upon that. In particular, we use a very well-known method in the computational linguistics and information retrieval literature called word-to-vec. I'll talk briefly about it. We use word-to-vec that is specifically trained on these WHO news bulletins over a large period of time because they help capture a lot of distributional context that's inherent in those bulletins. So here's an example of that first level of modeling that I mentioned that I said we'll get out of the way. We're going to be looking at age and gender extraction. And one of the easy parts to extracting age and gender is that these bulletins tend to describe them in a fairly structured way. So a simple hierarchy of regular expressions is able to capture them. So for example, they'll go ahead and say a 57-year-old male from Riyadh, a 48-year-old male, and so on. And so they're easy to extract. The only issue here is there might be multiple patients that are reported in a single report. So we'll need to make sure that we are not conflating reports from multiple patients into the same patient here. We typically do that by once identifying these phrases, marking that phrase or that following sentence as specific to that particular patient, and then try to see if any subsequent mention refers to the same patient or a different patient and so on. So this is how we extract age and gender. And like I said, we'll get this out of the way because there's not much of complications that we encounter for extracting this piece of information. It's the other aspects that get more complicated. And to do this, I need to take a detour to explain what word embeddings are. And this is a whole topic by itself. I won't be able to do justice to it today. But essentially, the idea of word embedding is words are defined by the company they keep. So if you want to understand a word, look at the words that are surrounding that word. The underlying hypothesis here is that words that occur in similar contexts tend to be similar. So for example, the words Clinton, Bush, Mandela, Reagan, and so on are similar because they tend to be found in similar contexts. In this case, contexts that have to do with what presidents do and say, and so on. The way word embeddings are designed is to think of how do we represent these words such that those representations capture the similarity in context in which they appear. So if two words are similar because they appear in similar contexts, it goes to say that they should have similar representations. So once you give me these representations, that automatically tells me that these words are similar and I can potentially substitute them in similar contexts and so on. Here's an example of how this word-to-vec method works. These methods take a large body of text. In this case, suppose you have an entire novel or you have a WHO bulletin or whatever. And here I'm looking at a particular word, in this case, will, and I'm looking at the context in which will appears. To the left of will, there is three words, let's say, where there is a, and to the right of will, there are three words, let's say there's a way. So the context for this will are these three words to the left and three words to the right. And it need not be three words, it could be 5 words, it could be 1 word, it could be any way in which we define context. So imagine going through a full corpus and listing out all the context for all the words that appear. And then essentially what these methods are doing is they're trying to learn mappings from the context to the words or from the words to the context. They go both ways. And they try to learn mappings such that this type of function is evident in them. And as a result, you'll notice when they actually come up with learning these mappings, these representations turn out to be really close to each other. So if two words are similar, it means that they should be replaceable in their context. This is the general idea for word-to-vec. And the good news is we don't have to learn these word-to-vec mappings ourselves. All the big companies like Google and Facebook have already trained these mappings on large collections of documents. And you have these pre-trained vectors for each of these words. You could potentially start with them. And in fact, that's what a lot of research in computational linguistics does. They start with pre-trained embeddings. Then they try to steer these embeddings to suit their purpose. For our case, we are trying to learn these embeddings to reflect a lot of medical language and vocabulary. And so what we do is we look at specifically these WHO bulletins and a lot of news articles about diseases and disease incidents and so on. So for us, the context is even more specific. It's context having to do with disease reports, disease incidents, and so on. So here's an example of how this would work in our case. So we use these pre-trained embeddings as input to some of our methods, and then we fine-tune them to suit our WHO news modeling and so on. So here are examples of sentences where you can see that similar words tend to appear in similar contexts. So the patient had no contact with animals. Instead of, you might hear the patient had no contact with camels. And that will tell you that people tend to use these two in similar contexts, at least for the purpose of these disease incidence reports, right? But maybe not in a different context. Animals and camels are too far apart in some other context. Similarly, a patient was hospitalized or a patient was admitted. That will give you similar context. So what we end up doing is we use word embeddings to try to identify similar contexts in which phrases and words are mentioned, and use that to expand our predictor list to find additional keywords and additional phrases to look for. So we use two types of these word-to-vec techniques. I'm not getting into the details of it, but I'm happy to talk about it after the presentation. So one of them is called a negative sampling technique, and the other is called a hierarchical softmax technique. You can think of them as different ways to train and learn these embeddings, and they have different properties. What we are doing here is we are trying to develop two different representations and then trying to understand how effective these representations are in extracting all those features that are of interest to us. So we use this full database of WHO news reports that I mentioned earlier. This is pertaining to all diseases, not just MERS, because this type of contextual information is useful and extractable in a lot of contexts, a lot of situations here. These articles are pre-processed, as I mentioned. And then the word embeddings are used as input to extract these features. In the first level algorithm that we talked about, we want to extract a lot of dates. We want to extract the date at which the patient developed symptoms, the date at which the patient was hospitalized, which is typically several days later when things get worse, and then the date at which the patient perhaps passed. We start with the seed predictors that I mentioned. And then we use these embeddings to try to expand these predictors to find additional phrases. And then we try to predict each one at a time. And then we also try to do multiple predictors to make these forecasts. So here's an example of how we might use these types of expansions. We start with a keyword like hospitalized, and then we expand them to additional keywords like shown here, hospitalized with a S, not a Z, screened, treated, diagnosed, admitted, and so on. And each of them gives you additional keywords to try to do the information extraction. And then we identify the sentences that mention that predictor. So once we expand them into certain keywords, then we look for the sentence that contains those keywords, those expanded keywords. We construct a dependency parse for that sentence. And then we try to compute the shortest distance between the predictor and some date that is mentioned in that sentence. So for example, if the sentence says he developed symptoms on 4th June and was admitted to a hospital on 12th June, we compute the distance between these phrases and those specific dates like 4th June and 12th June, and use that information used by a predictor to decide which date to output. In some cases, the shorter one is better. In some cases, the longer one would be better. There's a whole range of features that will go in to decide which one is most effective. We use each of these features as predictors and then try to find the date for them. Some of them will give you dates, some of them won't give you dates, and then you can do some form of aggregation on top of it. In this case, we are doing a simple majority vote, but it could be something else, and that majority vote is then extracted as the final output and then returned for this particular feature. For looking at the more advanced features, this is what we call the level 2 algorithm. So here we are trying to extract clinical features that are exhibited by that patient, trying to find out if they came into contact with any animals, if they come in contact with other patients, any other comorbidities, they have any special conditions and so on. And we go through the same sequence of steps here. We start with those seed predictors, we expand them to additional keywords, and then we try to predict each of them individually, and then we try to aggregate that into a final conclusion. For example, if we have a keyword like animals, the contextual similarity will give us other phrases, animal, camels, livestock, sheep, and so on, and use that to make a lot of expansions. One wrinkle here is that sometimes the sentences are actually sentences of no symptoms or lack of symptoms or lack of information. So in extracting information here, you need to look for negation, a lot of negation information that is explicitly represented here. So for example, if you look in our own medical records, you'll see the doctor might write statements like the patient has no sign of something, or the patient has no travel history to X, and so on. So in the same case, when the doctors interview the patients and then report this in these statements, they would say the patient has no comorbidities or no contact with animals and so on. And we look for direct negations like this. If there is no direct negation, we look for a lot of indirect negations from these dependency parsers. And only after all of these are filtered out, then we try to look for some of these explicit indicators of animal contact and so on. So here's an example of a lot of multiple predictors, again providing an output, and then that output getting aggregated into a single prediction here. So in general, the point I want to make is information extraction is pretty noisy, and there's a lot of dirtiness that goes with extracting all of this data. But we have a pipeline. We developed a pipeline for it based on all these considerations that I mentioned. So finally, we come to the point of trying to evaluate these line lists. To evaluate the line lists, we need to compare it to a ground truth data set. And our colleagues at Boston Children's Hospital Health Map, John Brownstein and his developed a hand-curated line list for MERS outbreaks in Saudi Arabia. So what that means is they had epidemiologists comb through individual news articles and then curate each of these pieces of information. So this was done completely independently from our group. And so they had a separate table of entries. And now we want to compare the extractions we have made against the extractions that the human epidemiologists have done here. The data set for this particular case goes from 2012 to 2015. And there are about 241 patients who are described across 64 reports. And not all patients have all the features that we are interested in. Sometimes the features are truly missing. Sometimes they could be present but not extracted. We're trying to do a best effort in terms of trying to compare what we have and what we're able to extract. The evaluation aspect of it is not trivial because, like I mentioned, you could have one report giving rise to multiple cases. So it's not a simple matter of accuracy that we would typically expect. What we end up doing is, on the left, you see each of these bubbles is a human entry. On the right is an entry that has been extracted by our algorithm. What you have is a set of entries here and another set of entries here. So the best way to match them is to do what is called a bipartite matching, because you don't know which entry is supposed to correspond to which ground truth entry. But you want to give the best effort credit for the algorithm to say that it really came up with an actual entry. Essentially, this becomes a bipartite matching problem. So on the left is all the ground truth cases, on the right is all your extractions. And then you create these edges, and the weight of these edges corresponds to the quality of the match between some ground truth entry and one of the extractions that you have. And you can't match a single entry to multiple entries on the right or vice versa. So what we are trying to do is what is called a maximum matching bipartite graph that optimizes this quality score, which are the weights along these edges. So the higher quality score means that you've done higher quality matches, and lower quality score is when you miss several aspects of it and so on. We're essentially creating this bipartite matching problem. All the algorithms outputs are on the right and all the ground truth cases are on the left, and then we're trying to distill it into a single numerical measure here. Once we do that, we also try to ask the question, where does this accuracy come from? Or where exactly are you losing points? Are you losing points in the demographics? Or are you losing points in the disease onset dates? Or are you losing point in comorbidities and so on? And it will also be the case that sometimes when you do this matching, there could be entries that we are not matching on the left. There could be entries we are not matching on the right. That will affect your precision and recall. And so we track that as well. We developed some baseline models. So the baseline models in this case are models that were originally supplied by our epidemiologists. So these are the basic features that they look for. So they start with one seed keyword, and we just use that one single seed keyword for extraction. We don't grow those seed keywords using our embeddings. And so this really will help us understand if these expansions are really useful in extracting information. And then we have our method gel here. That's really what we are comparing against. And as I mentioned, we have two variants of gel. They both have to do with how these embeddings are trained. One is the negative sampling method, NS. The other is the hierarchical softmax method. So first, let's talk about the quality score. This is the average quality score. The quality score is out of 1. So the baseline method is pretty reasonable. It gives you a starting score of 0.67. So using just the features provided by domain experts, you're able to get about 0.67. And this is the average. There are cases when the performance is much lower. You can see the distribution on the bottom. Using the expanded keywords, you can see an average improvement from 0.67 to 0.74. But this number does not reveal the case that for very specific cases, you can start showing some very significant improvement. So I'll show you some examples in the future slides. Here's a more detailed drill down of the performance with respect to specific features. For each of the features, we are trying to catalog what the improvement looks like from the baseline to the gel method. And as you can see, for certain features like the hospitalization date or the onset date, we show really significant improvement in terms of how gel is able to extract, and it just has to do with the linguistic variety in which people describe these features. It's pretty difficult to try to extract them with a very fixed seed set of keywords. And the actual variety in which people describe them is much richer. And so the overall performance across all these features really adds up. There are cases when the original baseline does better. We'll talk about that in a minute. But in general, these seed expansions turn out to be really useful in getting much better extractions. Here's some discussion in terms of the clinical features. So remember, clinical features are like the highest level of information extraction we are interested in, which is, did the patient come in contact with animals? Did they have other secondary contact, relations to healthcare workers, comorbidities, and so on? And you can see here, in overall, gel is very good at extracting comorbidities and relation to healthcare workers and so on, even animal contact. But In the case of secondary contact, the baseline method actually performs really well, much better than gel, which means that whatever we started out with as the seed set of features turns out to be pretty useful to be able to extract these features right from the get-go. That all these additional expansions that we are doing actually causes a deterioration in performance. Here is a little bit of a drill down. I'm sorry if the slide is a bit squished, but essentially it's showing you what are the informative predictors for each of these features that we're looking at. So onset date, hospitalization date, outcome date, animal contact, and so on. So as you can see, for each of these features, the most informative predictors are highlighted in this plot. So each bar here refers to one particular keyword. So for example, if you look at animal contact, this is looking at sheep, animals, rodents, and so on. And the word direct also appears because a lot of times people talk about the direct contact with animals. So direct turns out to be a very important feature for this. And similarly for hospitalization date and outcome date. This turns out to be very important going forward, trying to understand which features are most relevant for extracting each of these facets here. But keep in mind that we've done this analysis only for MERS in a particular region. A different disease in a different world region might very well lead to different conclusions in terms of what is informative. So we're still working on this, but we think of this as a starting point to information extraction in this domain. And our goal is to be able to do this at scale for a lot of other diseases and also other languages. A lot of the work here is starting with these WHO bulletins, which are pretty structured to begin with, but they're also scoped. But we want to also look at other languages in which these types of reports appear and be able to extract information for line lists from there. And we also want to extend the model to try to take into account more unstructured information. Right now, we're focusing only on WHO bulletins, but there are also news reports that arise, which do not pass through a medical filter or lens, as is the case with WHO. So these are more written in the form of news reports, and so might have elements of sensationalism and might even have inaccuracies. We want to generalize our model to be able to extract them. And one of the problems that we'll encounter there is when we do that, we also have to worry about duplicate detection. There could be multiple news articles reporting on the same incident. One of them might be giving the age of the patient, the other might be giving the gender of the patient. So we'll have to make a conclusion about whether these two are really referring to the same patient or different patients and so on. We need a lot more advanced techniques to be able to reconcile information across these multiple sources. And in all of them, we'll need more human annotated data going forward. But this is an area of active interest in our group. We continue to do information extraction in many different domains. So if any of you find this useful, relevant for your own work, let us know. Happy to collaborate. I'm happy to also provide you the code for this if you want to try it out on other data sets that you have access to.
Thanks so much, Naren. Great. As usual, very nice presentation. And let Golda take over and run the question answer session. Very nice. Thanks.
Sure, yeah. Thank you, Naren. Are there anybody who has a comment or a question for Naren? Anil, you can go ahead.
Yeah, hi Naren, very nice talk. Inputs that you consider here are from like news articles, right? Is that right?
Actually, so the WHO bulletins, so they're a little bit more, I would say, rigorous, structured than news articles.
Oh, okay. This is not speculative or anything.
No, it is not speculative. Correct. Okay. And they probably have gone through some level of quality control and so on. Like, for example, just the way it is described here, so-and-so male from Riyadh developed so-and-so and so on. It's already written in a fairly structured way, which may not be the case with news articles.
Oh, okay. And these are from, at least from this description, it's pretty clear that that is a relevant case, right? It's not, there's no doubt about that.
Oh, you mean, do we need to first filter to see
whether it is actually the particular disease you're looking at, or it's some other
I see,
confounding kind of thing?
Yeah, that's a good point. I guess we haven't focused on a region of the world or a time when there are multiple conflicting diseases. But yeah, it's a good question. So we should, like right now, right? If you want to look at COVID versus flu and trying to separate them, that's an important issue.
Yeah, thanks.
I see we have a question in the chat box. Irene asks, do you have any insights about the plan to aggregate CDC data in VHHS?
Actually, I don't. I don't. Madhav, I don't know if Brian is on the call.
Brian was. We should, Irene. I think we haven't done it. But at one point, James, one of our students, started building these line lists as well, very early on in the epidemic. And I think that project is stalled as of now. But I think it's a good question, and we can go back to CDC.
Issue, right? Because we needed some good amount of training data. So we had this particular data set that was developed by Brownstein's group, and that was useful. But again, here, like I said, we'll need some work to adapt it to COVID, especially if you want to talk about symptoms and so on.
No worries. I see one from Stephen. Does WHO have an epidemic investigation form that captures this data in a structured electronic form?
I know a lot of the crowdsourcing sites have tried to do this, but I don't know if it has made its way into an official structured form. You know, all the people who are trying to do participatory surveillance, they'll try to standardize this. I don't know. Madhav, do you know?
Not sure. Don't have a good thought on it, Naren.
I think Ira Longini was making tools for this kind of thing that you could use on a smartphone or something, where you could just gather this essential data and submit it without having to write a text report, which then, people have to parse later on.
Right.
In fact, I was going to ask that question with Ramanan also online, because I think in countries, say in a place like India, you might be able to get concise data set by just talking to people and convert it into line lists much faster. But I don't know what Ramanan feels about it.
You absolutely can. In fact, we have some access to this sort of line listing data as well. I mean, just to say, this is actually fascinating because we hadn't really looked at using this sort of natural language processing for this sort of work. I don't know how much is actually in this sort of text kind of format relative to already being in fairly tight tabular data sort of formats. There isn't really a culture of translating charts into, patient chart into electronic formats. And in fact, I was going to say that even in the US, you don't see it quite that often to see this sort of thing. You can get this from news reports, but when you're looking for large volumes of data, you really want to get this out of individual patient kind of information. So have you thought of what kind of data source might exist even in the US, this sort of descriptive information?
Yeah, so you're right. I think it depends on also, the level at which you want to go into the line listing. So many people just want to capture some very, very basic information. But then if you want to, depending on the disease that you're studying, you need to go further into detail.
Right. Naren, this is Brian. I can help fill in that. I mean, I think in the early days of an outbreak, this kind of descriptive information is plentiful. And even in this COVID outbreak, there was people that were aggregating all the way until there's about 10,000 or so of these kinds of sentences in a line list. And I think Cecile Vabode produced a publication that was analyzing that, which helped reveal some of the key epidemiological features, because getting this idea of what the incubation period is or how long the infectiousness is or certain risk factors for like some of the more severe outcomes is sort of what you're looking at. And at this stage, when there's millions of cases, et cetera, this kind of approach doesn't make as much sense. But what we saw in this previously with MERS, I think the WHO was actually publishing some of, not MERS, I guess this was, I think it was MERS that we did this with, right now.
This is MERS, yeah.
The WHO was producing these little summaries, and it was coming out of the Department of Health, I think, or the Ministry of Health. And you would just get these weird little blurbs. It's almost like a doctor's soap note that they would write, and you were getting them for each patient. So that sort of was the inspiration, I guess, for this tool. And again, I would just say in COVID, we were seeing these kinds of things. They weren't maybe like 3 or 4 sentences or maybe 1 or 2 sentences, but you were getting like age, gender, hospitalization time, initial sickness time, maybe where they lived, that kind of a thing. So you can get this in the early days, but at this stage, these line lists sort of lose their value because we're at population level concerns, but it can help give insights in the early stages, which is really important because a lot of our modeling assumptions depend heavily on some of these, what is the incubation period kind of assumptions.
Right. So in fact, Naren, I was also going to ask you, I missed the first couple of slides you had, and I know you work with John Brownstein, but have you tried running the ProMed daily news feed into your kind of algorithm to see whether you can pick up, say, I don't know, atypical pneumonias, to be able to park one set in buckets which are pretty standard, maybe drug-resistant infections, or maybe a case of, say, even plague, which you'll find every now and then, which you'll find on Health Map as well, but you find on ProMed. I know ProMed works closely with Health Map, so it's there. But the natural language stuff is there on the ProMed emails.
Yeah, in fact, we have a separate paper that is focusing on finding little clusters of disease incidents being reported, and what are the symptoms, what are the general vocabulary that gets reported along with it. So it's not so much about information extraction, but about looking for little atypical clusters of disease reports and then extract information. So we've done that with ProMed. So this particular one needs a little bit more scoping, right? Because you don't want to mix a MERS report with some other report and mix up all these things. So there's a lot of careful vetting going on before applying this algorithm, because when you're extracting a table like this, like shown here, you want to be really sure that you're focusing only on the disease of interest right now, and everything that's here is really pertaining to MERS and so on. There is that level of initial classification, if you will, to get to this point, right? So letting this loose on a larger context might, we have to be careful before we do that. So I can talk about that other thing at some other point, but there we are looking for more broad trends of disease incidents and what exactly is being reported in different hotspots across the world, and what are the symptoms. Because every now and then, John will get a report that says there's a mysterious disease being reported in Singapore, and nobody knows what it is, and people are showing these symptoms and so on. And sometimes it becomes clarified in a day or two what that patient really had, but sometimes it really sticks out like a unclassifiable thing. And so for those types of things, it's really important. Like Brian said, at least in the first few days, you want to get a handle on what really is going on in this place, and so on.
Can you do the same thing, say, for COVID, for instance? So let's say there were atypical, I don't know, coughs or whatever it is going back to November or December in China itself or other countries. Can we use something like this potentially to parse out everything else that you can actually attribute a cause to, and then be able to identify whether there was a pattern and things that might have looked like COVID going back that far? Remember, others have tried to do it based on sewage samples and things like that. But I don't know if anyone's thought of doing this with ProMed. And ProMed, by the way, John is also very involved, but I also sit on the governing council of ISID, which runs ProMed. So we can have a very formal tie-up with ProMed to do this stuff, and they can provide all of their past records at one go.
You're very good, actually, Ramanan. I think it's a good idea.
Shall we do that? I can get that sorted out.
Yeah, we can follow up. So, but to answer your question, no, we haven't done that. So I think what you're saying is, think of this as a way to do some triaging of things that are unable to get classified, start putting them in a bucket, maybe for manual inspection, further manual inspection or something. Yeah.
I mean, if we can find if there were clusters that were inexplicable more in that period, November, December, or October, November, December, than in the previous 6 months or whatever else it is, which might indicate that this was out there already, but we just couldn't attribute a cause to it. It might help us also going forward.
Yeah.
Sure. That's a really, really good idea. I would be very interested in any results because, in fact, we're doing some of the sewage detection, and it would be fascinating to try to tie some of that together. So I'd be very interested in whatever results you pick up.
Are you doing sewage in just some places, Rita, or is this in a number of countries?
We're collaborating with several states And in fact, yes, another country as well, Italy, for one.
Okay.
It's a great project for us to undertake as a part of Expedition. So, Ramanan, thanks for bringing it up. In fact, it also suggests this multi-sensor kind of aspect where there's sewage data and there's more text data. And I think you'll start getting very interesting signals when you're combining it together in a meaningful way.
Yeah, I agree.
I think that Chris had a related question.
Right. Naren, it was a really interesting talk. You may have covered this, and it's a little bit narrower than the last conversation, but so sometimes a given event could be, for example, rebroadcast or repeated from another source. And so this question comes in a couple stages, but I'm just going to ask them all and then be quiet. So it seems to me that might be possible at least. And so I just wondered if there's any way to not accidentally multiply count things. Like you can even imagine this is as a problem of countermeasures for some kinds of circumstances, I suppose. The second question is somewhat related to that is both within and between sentences, how do you handle pronoun reference when you so for example, we have the patient and we have he, and at the beginning we have a 57-year-old male, and it's apparent to us, of course, that it relates to that, but I'm a little, I'm interested in how you handle that, not just within a sentence or between sentences or within lines and between lines. Between lines, it becomes related to this issue potentially of multiple reports. Anyway, so that's my question.
Right. Yeah, so that's a very well-studied problem in NLP to know whether this sentence is a continuation of the previous one and who this subject refers to. So the disambiguation is a very standard issue. I mean, we haven't done any new research in that space, but we've employed a lot of best practices that people have done here. So the example that you found, all of these things have, the patient. And so, we should know by this reference that the patient does not mean a new patient. It really means the same patient that was being talked about in the previous sentence. So there's a lot of standard NLP approaches to address that. And then, as you mentioned, if a paragraph or if a report is talking about multiple patients, we need to know when the description of the first patient ends and when the second patient begins. And that, there's a lot of approaches for that as well, where people talk about, it's not very different from these text styling algorithms that try to decide where to introduce a paragraph break. And when the subject matter is sufficiently different from the previous paragraph and so on. So these are, sort of best practices in the information extraction literature that we are just adapting here. The first question you raised, Chris, I think that was more about the duplicate detection or the counting, right?
Yes, and I mean, it's related in that if you have two lines, do they refer to the same person? Even this is
right.
A different version of the other one.
Right. Yeah. So when we did this work, I mean, this area has grown by leaps and bounds. So when this paper was published, this was the state of the art at that time. But things have progressed very rapidly since then. I mean, one of the ways in which if I were to address this problem today, I think the way to do it is to use a lot of the newest research in question answering towards this. Like, for example, feed this paragraph to an algorithm and then ask questions like, who was the patient? How old was the patient? What gender was the patient? And so on. And there are a lot of methods that try to distill information across sentences to answer questions. And so we might take an approach like that. But right now, like I said, we're also piggybacking on the fact that these WHO reports are a little bit more structured and more predictable than general news reports. Like Ramanan was saying, I think those would be much more difficult and there'll be more variety, and the information would also be distributed all across the document. Like you might find a piece of information in paragraph 1, and then you might have to skip a couple of paragraphs to find the next piece of information. Not too different from how we manually scan news reports, right? We quickly scan through to see what's going on in a particular report. It'll be the same type of situation. So we are exploiting a lot of regularities here, definitely, no doubt about it, for this particular work.
Okay, well, we're just a couple of minutes past 12:30, which is our official end time. So I guess we'll cut it off here. Just want to say thank you to Naren for a great talk and for everybody for the discussion. Manav, do you have anything else? Okay.
Excellent talk, Naren. I had a lot of questions, but I'll ask later in the interest of time. But I really enjoyed the talk and different flavor. So thanks again. Yeah.
Just a reminder to everybody, our next talk is 2 weeks from today, August 27th, and we'll have Kathy Alexander, also from Virginia Tech, speaking then. So hope to see everyone there.
Great. Thank you very much, Golda. Thanks, Naren. Bye.
Bye, everyone.
Bye.